Welcome to the deep dive. Today, we're looking at decision trees, really useful tool in data science machine learning.
Yep, definitely.
We're drawing on some material from MIT's Institute for Data Systems and Society. And the plan is, well, to give you, the learner, a quick handle on what these are, why they're important, and, how they basically work.
Think of it as your quick guide. We want you to get the core idea of how these trees make decisions, the stuff that makes them tick.
Okay, so let's jump right in. What is a decision tree exactly?
Well, picture a flowchart. That's probably the easiest way to think about it.
Right, a flowchart.
Yeah, and at each step, each sort of junction, technically called an internal node,
Okay.
you ask a question about your data, a test on a specific feature.
Like, income for a loan application.
Exactly like that. Is income above X? Yes or no? Each answer takes you down a different branch
And you keep following the branches, answering questions.
until you hit an endpoint, a leaf node.
And that leaf node is the final answer, like loan approved.
Precisely. Or loan denied. So the whole path you took, that's basically a rule derived from the data.
Huh. It does sound a bit like how we make decisions, step by step.
It really does. That's one of their biggest strengths, actually. They mirror human reasoning in a way that feels, well, intuitive.
And that makes them easy to understand, right? You can actually see the logic. It's not a black box.
Exactly. We call it interpretable or open box.
Yeah.
You see how the decision was made? That's huge.
What else makes them useful?
Well, they're pretty versatile. They can handle different types of data numbers, categories, that sort of thing.
Okay.
And they can model quite complex relationships without needing loads of data pre-processing.
Less cleanup beforehand. That's always good.
Definitely. And they work well with large data sets. Plus, they kind of automatically figure out which features are most important for the decision.
Oh, like feature selection built in?
Yeah, the process itself highlights what matters most in the data.
But like anything, I assume they have downsides, limitations.
Oh, for sure. They're not perfect. One thing is instability.
Instability. How so?
Well, sometimes even small tweaks to the input data can result in a completely different tree structure.
Really? So the predictions might change quite a bit.
They might, yeah. It's something to be aware of. Also, finding the absolute mathematically perfect decision tree, that's computationally really hard.
Too hard for computers.
For practical purposes, often yes. It's what we call NP-complete. So the algorithms we use to build them are typically greedy,
Greedy meaning.
meaning they make the best-looking choice at each individual step without looking ahead to see if it leads to the overall best tree. It's efficient, but not guaranteed to be optimal.
Okay, so it's a practical shortcut.
Right. And another big one is overfitting.
Ah, overfitting,
Yeah.
where it learns the training data too well.
Exactly. It learns the noise and the specific quirks of the data it saw during training, so it doesn't perform well on new unseen data.
Like memorizing answers instead of understanding the subject.
That's a great analogy.
Yeah,
There are ways to combat it, like pruning the tree.
cutting back branches.
Yep. Or using more advanced techniques like random forests, which combine multiple trees. But that's maybe for another time.
Right, so just to recap quickly, decision trees are easy to understand. Versatile classifiers, creating rules from data.
But they can be unstable and might overfit the training data if you're not careful.
Okay, so what's the logic underneath building one? How does it decide which question to ask at each step?
Good question. It boils down to reducing uncertainty or impurity in the data.
Impurity.
Yeah. Imagine you have a mixed bag of data points leading to different outcomes. It's impure. The goal is to split the data at each step in a way that makes the resulting groups as pure as possible, ideally. Groups containing mostly one outcome.
How does it measure that purity or impurity?
A common way is using a concept called entropy. Think of it like a measure of disorder or randomness.
Okay, low entropy means less disorder, more purity.
Exactly. A group with all the same outcome has zero entropy. A group with a 50-50 split has high entropy.
So the tree wants to lower the entropy.
Precisely. At each node, the algorithm looks at all the possible features it could split on, like age, income, whatever.
Right.
And it chooses the feature that results in the biggest reduction in entropy after the split. We call this maximizing information gain.
Information gain. So it picks the question that gives the most clarity, that best separates the outcomes.
You got it. It's that greedy approach. Again, pick the split that provides the most information, the biggest reduction in uncertainty right now.
It's like sorting things efficiently. You tackle the easiest, most obvious separation first.
That's a good way to put it. You split based on what clarifies the situation the most at that point.
Makes sense. Reducing uncertainty seems like a pretty fundamental idea.
It really is. And decision trees just give us a very visual, understandable way of seeing that process applied to data.
Cool. Okay, so final thought for you, our listener. Since these trees break complex decisions down into simpler sequential questions, think about a complex choice or situation in your own life. Could you try mapping it out like a decision tree? What would be your key questions, your features at each step?
It might give you a new way to structure your thinking about it.
Absolutely. Something to ponder. Thanks for joining us for this deep dive.